Okay, so I see it's time for us to start the session. Can everyone hear me well? All right, so welcome to the dynamic analysis session for ICSE 2022 demonstration track. In this track, today we have three papers. Each paper we are going to have 15 minutes for its presentation, demonstration, and Q&A. For those who would like to ask questions about this paper, please try to post those questions in the chat box. And once it's time for the Q&A, I will make sure that I queue those who ask questions. If you are willing to turn on your audio and the video to ask a question yourselves, please do so. Otherwise, I will read the question you also receive. All right, so let's start the presentation of our first paper. Our first paper is a presentation of the school minor. And the paper will be presented by Yu Gao. Please come.
Okay. I will start my presentation. Hello, I'm from Institute of Software, Chinese Academy of Sciences. I'm going to introduce our work, Common Data Guided Crash Injection for Cloud Systems. For modern cloud systems, node crashes are always inevitable. A node in a cloud system can crash due to a variety of reasons. To combat node crashes and support high availability and high reliability for end users, developers introduce various crash recovery mechanisms into cloud systems. In other words, modern cloud systems are designed to tolerate crashes of partial nodes. However, those crash recovery mechanisms and their corresponding implementations can be buggy and result in catastrophic failures. We refer bugs that lie in incorrect crash recovery code as crash recovery bugs. First, let me use a real-world bug from Zookeeper to explicate how a node crash eventually triggers a crash recovery bug. During the leader-follower synchronization process, the current epoch value 2 or the leader side is first persisted to the snapshot file through the I/O operation 3. That epoch of value is stored to the current epoch file through another I/O operation, operation 4. Here, operation 3 and operation 4 store the common data epoch or the leader side to two different local files. When follower crashes between operation 3 and operation 4, the newest epoch value stored in the snapshot file and the epoch value stored in the current epoch file will be inconsistent. When we restart the follower node, it will read inconsistent epoch value from these two files and kill itself. Therefore, a crash recovery bug occurs. As shown in the previous example, a node in the cloud system can store a piece of data in multiple places. For example, a node can store data to another node through messages. A node can also store data to different paths in a storage system. We refer a pair of I/O operations that store common data to different places as a related operation pair. The node crashes that happen at a specific time can leave a cloud system in inconsistent states. Crash recovery bugs are more likely to occur in these inconsistent states. To detect crash recovery bugs triggered by inconsistent states, we propose a novel approach, dminer. First, dminer traces code usage at runtime. Second, dminer identifies related operation pairs that store common data to different places in a system RA based on the execution trace. Finally, dminer performs crash reboot injection testing according to the identified related operation pairs. In first step, dminer tracks data flows in a system RA based on dynamic state propagation. That every I/O write operation and its corresponding information will be recorded as the execution trace. In second step, dminer analyzes execution trees to identify related operation pairs that are performed by the same node, use common data, and have different storage destinations. In third step, dminer injects crashes and corresponding reboots to interrupt the execution of related operation pairs. That dminer uses predefined checkers to check failure symptoms to confirm crash recovery bugs. Our predefined checkers check both general failures such as node crashes and operation-specific failures such as returning error code. If the current test fails to pass the checkers, dminer will generate a bug report. We implement our dminer approach as a command line tool, and it's easy to use dminer. Testers only need to modify some related configurations and run several commands. We evaluate dminer's effectiveness in detecting crash recovery bugs on 3 widely used open source distributed systems. And the dminer has detected 5 unknown bugs and 1 known bug. These bugs can cause cluster out of service node downtime, operation failure, data sterilness, and misleading error messages. That's all. Thank you. Any questions?
I think you can go ahead with the demonstration. If you want to play the video, you can do it now. Then we will follow by the questions.
Okay. I will use our video to show how to use dminer. Okay, to use dminer, we first need to run several commands to generate a instrumented version of the runtime environment. We should configure every node in the Zookeeper cluster to use the instrumented JRE and include the dminer as the Java agent with a JVM argument. Now we can run the workload and tracing execution traces from every node in the cluster. Now we can run a command to perform output rigid operation pairs and to be tested. We use predefined checkers to check failure symptoms as we have presented. Now we can configure the target system to run at the triggering mode. We now start the fault injection engine to perform crash injection testing. Here we can specify the test range. Okay. As shown in the video, dminer will generate a bug report for the test that does not pass the bug checkers. That's all. Thank you.
All right. Let's thank you for the presentation and demonstration. So it's time for questions. So I see a question from Didier. Please go ahead and unmute yourself and ask also the questions.
Thank you for your presentation. So I wanted to, I read the tool paper and I have limited knowledge on crash injection, but it seems like there's a lot of work on crash injections. So my question is there a benchmark of known bugs that can be used to evaluate work such as dminer? Like maybe that could help identify general cases in which dminer reports false positives or maybe just fails.
Yes. dminer focused on different types of crash recovery bugs from other crash recovery bug detection work. dminer mainly focus on the crash recovery bugs as shown in the presentation. dminer focus on the crash recovery bugs that are triggered by inconsistent system states. Other approaches are not effective enough in detecting such kind of crash recovery bugs.
Any other questions from the audience? Please feel free to unmute yourself and present the questions. So I have one actually to follow up on your answer. So it looks like in your paper you deal with the mainly focus on inconsistent system states. I'm wondering if there are other scenarios that can trigger other kinds of crash recovery bugs, and can you think of using dminer to handle these other cases? I understand that probably requires some extension. I'm just curious if you can elaborate to see if this tool can be extended or expanded to handle these other kinds of crash recovery bugs.
I'm sorry, I can't really hear your voice. Could you please send your question or the chat room?
Can you not hear me?
Yeah, sometimes I can't hear.
Any other questions from the audience, maybe, until I fix my audio issue? Can you hear me now? Rejoin the room. I hope this fixed the audio issue. Can you hear me now?
Oh, yes, I can hear you now.
Yeah, so my question is regarding, following up on your answer on the current tool currently handles inconsistent system states. I'm curious that since there exist other kinds of scenarios that can trigger crash recovery bugs, can you talk about if dminer can be extended to handle these other scenarios, not necessarily those bugs triggered by inconsistent system states?
I'm sorry, I lost my connection for a while.
Let me repeat it. So my question is that can you think of applying dminer to handle other scenarios that can trigger crash recovery bugs beyond inconsistent system states?
I don't really understand your question. Do you mean dminer can be applied in other distributed systems except for
I'm talking about applying dminer to other kinds of crash recovery bugs beyond those that are triggered by inconsistent system states.
I think dminer may be useful since it's a faulty injection tool, and maybe it will trigger other kinds of crash recovery bugs, but we don't know the reason because it is designed to trigger crash recovery bugs that are caused due to the inconsistent states caused in our crash scenarios.
Mm-hmm. Okay, let me follow up with another question if there are no questions from the audience. So in part of dminer, you have a mechanism that decide if a crash could be triggered, right? So I'm wondering, using the heuristics that you used, is it possible that you have false negatives?
Yes, it has false negatives. The false negatives, we just leave it as a limitation of our work.
Okay, thank you.
Since you know, dminer can detect all types of crash recovery bugs.
Yeah. Can you
Any
give
other
us
question?
an example of a false negative scenario? Like what would cause it?
Could you pardon?
So in the paper, there are examples of false positives and what basically caused those false positives. Can you give us an example of what would cause a false negative?
The reason that causes false negative is because our dminer is designed to handle such crash scenarios we show in our presentation. So, for example, there are some kinds of crash recovery bugs that are caused by lacking of backup. So, dminer can't detect such kind of crash recovery bugs. And also some crash recovery bugs that are caused by incorrect crash detection mechanisms that can also be omitted by our approach.
Okay, thank you for the answers. I think we're running out of time for the first paper. Let's thank you again for all the presentations. So let's move on to the second paper.
Okay.
So our second paper is going to be presented by Didier, and he will present a tool called Dynaplex. Please go ahead.
Okay. Just to make sure you can all see my screen, right? Correct? Hello?
Yes, I can see the slide.
Okay. My name is Didier Ishime. I'm going to talk about Dynaplex, a tool to infer asymptotic runtime complexity of recursive program. So runtime complexity analysis can help detect performance vulnerabilities. For example, if a developer is expecting an implementation that runs in quadratic time and theoretically, but then the actual implementation turns out to run in cubic time. That's a performance vulnerability. Dynaplex uses dynamic analysis to infer recurrence relations and solve them for runtime complexity. So recurrence relations, or simply recurrences, are mathematical relations that show, for our purpose, how to solve a problem in terms of solving its subproblems. So for example, selection sort is an algorithm that sorts n element by recursively sorting n minus 1 element, and with at most n steps per recursive step, at most n operations per recursive step. Similarly, for Fibonacci sequence, you can find the next Fibonacci number by calculating the last two Fibonacci numbers. We use recurrence relations because even linear recurrences, which are simple enough because they only contain linear terms, are expressive enough to capture non-trivial program complexities. For example, binary search, which has a logarithmic complexity, can be captured by linear divide and conquer recurrence. The Karatsuba multiplication algorithm, which has an irrational degree, a polynomial with an irrational degree, can also be expressed using a divide and conquer linear recurrence. So linear recurrence can express program complexities from linear to exponential, logarithmic, and so on.
So sorry for the interruption. I don't know if it's just me or everybody else. I don't see the slides being moved.
The slides are not moving?
Yeah, I only see the first slide.
Oh, okay, sorry. Maybe it's because I'm in presenter mode.
I think that you're sharing the wrong window.
Am I?
You might be sharing, you might just need to share.
Okay,
So
yeah,
we
yeah.
can see that the PowerPoint and all the slides.
Okay, let me check. How about now?
Yeah, I see the introduction slide now.
Okay,
Yes.
so as I was saying, we use linear recurrence. I just want to quickly show the examples I was talking about. We use linear recurrence because they are expressive enough to express different complexities from logarithmic, polynomial, exponential, and so on. So Dynaplex works on analyzes program by basically instrumenting a program to collect traces and run the program to produce those traces. We run programs on random inputs, randomly generated inputs. And from those traces, we can infer recurrences and solve those recurrences using some pattern matching techniques such as master theorem. So here is an example of how Dynaplex works. The tree on the right is produced by running a merge sort program on a list of 7 elements. So at each node, starting at the first node, we have n, which is the size of the input, and id, which is the unique ID of the recursive call. So running merge sort on 7 elements, merge sort divides the list into 2 parts, one with 3 elements and another with 4 elements. Well, the IDs, they are changed to stay unique. But the most important thing here is the size. And as you can see, there's 2 child per node, and the size is getting divided almost by 2. So Dynaplex takes these traces and it computes the ratio between the size of input at a current node and the size of input at its child nodes. So with the left child, we have, for example, from the root node, we have 7 divided by 3, and 3 divided by 1, 2 divided by 1, and so on. And with the right child nodes, we have 7 divided by 4, 4 divided by 2, 2 divided by 1, and so on. And from this list, we can use regression to find this ratio that it tends towards 2, 7 divided by 3, and so on. So we also, as I said, we also count the number of operations per recursive call, which is represented on the left by this Fn part. Dynaplex uses polynomial regression to count the number of operations, and there are some heuristics to make sure that we get the correct relationship. I will show a link to the original research paper for those heuristics, but we don't have enough time to explain those right now. So after we compute that relationship, we have a complete recurrence relation, which then can be solved using master theorem to find out the complexity of merge sort is n log n. So I would like to also show how to use Dynaplex. Dynaplex is implemented in Python, and as I said, we use regression to learn some polynomial relations. Dynaplex work on execution traces, so it's language agnostic. You can analyze any program as long as you instrument it to collect the required traces. To use Dynaplex, all you need is a system that can run Docker, and you can pull the image from Docker Hub. At the end, I will have all the links necessary, and you can run all the experiments that we've run inside the Docker. You can produce your own programs in there, but there's also a GitHub repo where you can pull the source code and just compile it. So as I said, Dynaplex work on execution traces. So one of the most important part of the analysis is trace collection. We instrument the program to analyze, and we instrument it to collect the size of input and the depth of recursion at each recursive iteration. We also collect the number of loop iteration for one recursive call. These traces are saved in files using file naming convention explained on the GitHub. So these are the links. We have the GitHub link where there is all the readmes and all the instructions. And you can also use the Docker we have from Zenodo. And we have the extended research paper from Uppsala last year, which explains in detail the techniques used. Any questions before I get on with the demonstration?
Please go ahead with the demonstration.
Okay. So let's look at an example of how to instrument we have here, let me make sure I'm sharing the right screen. Okay. We have a C++ implementation of PancakeSort. We've developed an instrumentation library for C++, which comes included with the source code on line 1. So all you have to do to run the analysis is to include the library. And so the function to analyze here is PancakeSort. Where is it? Okay, so at the function entry on line 36, we collect the problem size n, so the rectrace function with the parameter n representing the problem size. And for each auxiliary function on line 42 and 43, or each loop, we also collect the number of loop iterations. So this one, operation counter, line 27. And so we run the program a few times to collect the traces. We have this script to generate traces for C++ programs, where you just run the program, it's already compiled, run the program on 100 times on input of size from 1 to 500, randomly generated inputs. So in this case, we have a seed which is saved for reproduction purposes, and that's taking longer than I thought. And we generate traces which are then saved using excuse me. So let me show you. The traces collected are saved using the file naming convention. So we have output and dash the size of the input used to produce those traces. We can, I ran the wrong program. I ran quick select instead. I was showing PancakeSort, but same thing. So the input, let's see if I can run the right one. The traces are saved in this folder, traces quick select or traces PancakeSort, and the file are named according to the size of the input. Okay. We can then run the analysis by calling the analyzer and passing it the trace file, the trace folder. PancakeSort. Okay, it's taking longer than I expected.
So this is a reminder for 1 minute to wrap up the demonstration.
Okay, so the output is divided into 3 parts. First, the analyzer computes the recurrence relation, which is for PancakeSort Tn-1. So just the recurrence term of the recurrence relation, which is Tn-1. And then it also computes the polynomial relation between the size of input and the number of loop iterations or operations, which is linear here. Then the 2 terms are combined, the recursive term and the non-recursive term are combined and then solved for the actual complexity. So we also, as I said, Dynaplex is language agnostic. So we also have other programs written in different languages. For example, if I can show one example using Python, let's see, merge sort. So in this case, we don't have a library to instrument all of the languages possible, but I will use this example to show how the instrumentation is done manually. As I said, we collect the depth and size of input. So line 17. The function entry, we collect the size and depth of recursion. And for each loop, line 36, there's a while loop. We collect the number of loop iterations or operations, and then we run this function a few hundred times to correct enough traces to run the analysis. I think that's all for the demo.
All right, let's thank Didier for the presentation and demonstration. I'm not turning on my video because I'm hearing some echoes whenever I turn on it. So please go ahead, post your questions, or unmute yourself and ask Didier the questions directly. So let me lead with a question from myself. So since you are developing a dynamic analysis, so assume that the quality of the inputs would have some effect on your tool's ability to correctly or accurately infer the complexity. So can you elaborate on that in terms of what kind of inputs you're expecting for this tool to accurately infer the complexity?
Yes. So Dynaplex takes, you can use random inputs. From our experiments, you can read more from the extended research paper, the last link. But in general, randomly generated inputs are sufficient enough, because if you collect the traces by running the program a few hundred times, the traces are going to be rich enough to contain the worst case complexity in most cases. In some cases, for example, quicksort, where the worst case only happens a few times, it might not be possible, but in most cases, randomly generated inputs are enough to produce correct results.
I see. Any questions from the audience?
Also, one other thing is that a lot of recursive programs, like let's say MergeSort or Fibonacci or Factorio, if they subtract a constant, they always subtract the same constant. So if the recursive call is not guarded by a condition, then it doesn't matter if you use random inputs or sophisticated inputs, since there is no guarding the recursive call, and the size always change similarly. Either it's divided by a constant or you subtract a constant.
I see, that makes sense. But to follow up on that, assume there are certain procedures that do depend on the inputs, right? And I'm curious, again, given that this is a dynamic analysis, probably it isn't sound. So you may have inaccuracy. So can you talk about the scenario where you actually would have inaccuracy, even if you have sufficient number of inputs generated randomly?
Yes. So, and like I said, the one example is quicksort, which in the worst case, when the pivot is let's say the first number, it's going to solve the least minus one element in the worst case. But if it's a randomly generated pivot, then the worst case doesn't happen that often. So even if you have a lot of inputs, you might not get the correct recurrence, since the worst case might only happen once in 1,000 runs. And since in some areas we are using regression, then that's going to get ignored. And in that case, we are working on other techniques to help improve Dynaplex in cases where the worst case doesn't happen quite often, like in Quicksort or programs similar to Quicksort, like if the recursive call is guarded by a condition.
I see. Yeah, thank you for the answer. We may have time for one more question from our audience, if any. Seems we don't have any more questions. Well, let's thank Didier again for the presentation. And congratulations on the excellent work. All right, so let's move on to the last paper of this session. So this paper will be presented by Xiao Qin from Washington State University, and the tool's name is DistFacts. Please go ahead.
Okay. Consume. Hello everyone, I'm Xiaoqin Fu. In this demo, I will demonstrate how users benefit from my tool. Before the tool demonstration, let me give you some background and context. In software management, there are two types of metrics, static and dynamic. Static metrics are easier to compute but are not suitable for measuring the dynamic behaviors of software. Dynamic metrics are more precise than static metrics. In this work, I focus on measuring IPC through dynamic metrics for distributed systems. Our tool computes two kinds of inter-process communications, 5 for runtime message coupling, runtime class coupling, class central coupling, inter-process reuse, and class management load, and 1 for process level cohesion. All these metrics together capture IPC behaviors of distributed systems at runtime. First, let's look at the RMC. In distributed systems, there are many messages passing among components. RMC measures the runtime message coupling. The more messages, the higher RMC. It indicates the runtime interactive activity among system components and communication cores. It could be used for assessing the understandability of distributed systems. I compute the RMC at both process level and system level. In process level RMC, between two given processes, PI and PJ, is the number of messages sent from one process PI to the other process PJ. Based on process level RMC, the system level RMC is the average of all process level RMC. Suppose that there are n processes. I have n times n minus 1 inter-process pairs. The next IPC metric I introduced is RCC, runtime class coupling. It measures IPC coupling intended of the extender to which methods from a class in one process relying on or interacting with methods from a class in another process. RCC indicates functional interdependencies. and it can be used for assignmentability. I define and compute RCC at the class level, process level, and system level. In class level, RCC is the ratio of two numbers. The numerator is the total number of methods in the first class that is depends on only method in another class in a different process. The denominator is the total number of methods in only process other than the first process that is dependent on only method in the second process. Here, DS denotes the dependency set of a method M. Based on the class level RCC, the process level RCC for a pair of process PI and PJ is the sum of RCC between only two classes across the two processes. Furthermore, the system level RCC metric is the average of all process level RCCs over all the n times n minus 1 pairs of processes, given the n processes in the system. The CCC metric class central coupling is similar to the centrality of a network, a metric in network measurement to identify the important nodes. Accordingly, it may be used to identify functional highly important classes in inter-process executions. Therefore, RCC can be used as a functional correctness metric. I define CCC at two levels, class level and system level. The class level CCC for class A in process PI is the sum of all RCC of all possible class pairs, which one class is A and another in a process other than PI. The system level RCC is the mean of class level CCC, measures for all classes over all processes. The IPR inter-process are reused. The idea is to qualify functional overlapping and code reuse in terms of IPC coupling. I define and compute IPR at the method level and system level. The method level IPR for method M in process PI is the ratio of the intersection of the local dependent set and the remote dependent set of M to the size of the entire interset of covered methods in all processes. The system level IPR is the ratio of the sum of the method level IPR measures overall methods in the system execution to the size of the entire set of these methods. The fifth IPC metric I introduced is CCL, class communication load. The idea is to measure the communication loads of a class communicating with others in all remote processes. I define and compute CCL at the class level and system level. The class level CCL for a class in a process is the ratio of the sum of the size of remote dependent sets of the class methods to the size of the set of all executed methods in the class. The system level CCL is the mean of class level CCL, measures overall classes executed across all processes. The last IPC metric I introduced is PLC, process level cohesion. The idea is to measure internal connections within a process. I define and compute PLC at the process level and the system level. The process level PLC for a process is the ratio of the sum of the size of local dependencies of the process matrix to the size of the set of all executed matrix methods in the process. The system level PLC is the mean of process level PLC measures overall processes. This fact also uses 5 quality metrics: execution time, cyclomatic complexity, information flow path count, information flow path length, and attack surface for different quality characteristics and their relevant sub-characteristics. This fact takes 2 inputs, including distributed system D and its runtime input T. With these 2 inputs, there are 4 phases: instrumentation, tracing, characterization, and classification. The fourth phase instruments the system to proper methods for monitoring method execution events. And after that, in the second phase, during the tracing, this fact performs the executions of the system. It traces and records execution events. This fact also computes different quality metrics. Based on execution events, this fact has the characterization phase. It computes all 6 IPC metrics. Using this IPC metric and quality metric results, this fact computes correlations between them. In the last phase, this fact utilizes learning-based classifiers to predict the high-level status of the quality matrix of the system. The output of a classifier is one of the 2 categories, high or low, indicating the system's quality being abnormal or normal. I use Python programs to perform k-means unsupervised learning with holdout validations and 10-fold cross validations. And I use VCA to perform buggy supervised learning to classify quality metrics. The evaluation results demonstrate the correlations between IPC metrics and quality metrics, and classification effectiveness, including precision, recall, and F1. You can get the tool from the edges. Thanks for your attention and time.
All right, so let's thank Xiaoqing for the presentation. Any questions?
And I can, you say, please.
Can we know which IPC metrics are more important in measuring the quality of distributed softwares?
You can see this figure. You see the I see the CCC is the most important according to the figure. You say CCC has the strongest correlations between quality metrics. You see.
Okay. Okay, thank you.
Okay.
Do you plan to do a demonstration? We may have time for 2 minutes demonstration really quick.
Okay, I see.
Now I will show how to install the tool. First, we download
I download the files from the edges.
So we don't see the screen that you're playing.
copy all needed files.
Let's see. It is changed.
So we only have 2 minutes for demo, given
Yeah,
that.
Quickly, I will very quick. Can you see it?
Now I will show how to install.
No,
will show.
I'm seeing it.
Download
No.
the files from this.
Can you see?
Yeah, I think I see it. Yes.
Yeah. First, I download the files from this trace, and we download and install an example, Apache Swift. I developed a calculator application using Swift. I should compare the application firstly. The first phase is instrumentation to insert purpose to monitor method events. We see the instrumented system files. The second phase is tracing. In this phase, I execute the instrumented subject. The shell stars are Swift server and a client. And from this result, I compute the IPC matrix. Yes, there are IPC matrix values, and then I compute the quality matrix. I also use source code lines to normalize the quality matrix. In the last phase, I use Python programs to perform unsupervised learning and supervised learning. The key means. And I use VCA to perform bugging supervised learning to classify quality metrics. Okay, my demo is over.
For demonstration.
Thank you.
I think we're running out of time for this session. Let's thank all the speakers again for their excellent presentations, and I hope you're enjoying the rest of ICSE.
Thank you.
Thank you.
Thank you.
I hope I will see you around in other sessions. Bye.
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 Bye.